Hey everybody, welcome back to Adventures in Machine Learning. I'm one of your two hosts, Ben Wilson, joined with
Michael Burke. Hi everyone.
Yeah, today we're going to be having a bit of a discussion on something that's near and dear to my heart, something I've been working on for many, many years, and it's talking about platform execution. And we want to discuss what's all about doing machine learning on Apache Spark, and what are the benefits, discuss how to do it, what are the different ways that you can do it, why should you think about doing it, and when should you do it. So
yeah, that sounds great to me.
So you had some questions you'd like to discuss, Michael. Go ahead and take it away, man.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story, about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv, and I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Yeah, so I think we'll use the standard format where I ask dumb questions and Ben answers them with wisdom and poise. It's worked out well in the past. So for starters, a lot of operations theoretically can run on one core using loops and non-vectorized methods. And Spark a while back came onto the scene and really transformed a lot of MapReduce operations and Hadoop operations. And it's now sort of the industry standard for parallelized computing, both for ML, ETL, streaming, and all sorts of things. So Ben, can you concisely say what Spark is?
Ooh. I mean, you kind of covered it in that intro, as in Spark is an evolutionary step on top of the MapReduce paradigm that was introduced by Yahoo and a bunch of universities when they created the Hadoop system, which that was a stepping stone from previous iterations of processing, like basically massively parallel processing systems. And Spark's departure from Hadoop is in the way that it does its computation. Instead of it being a disk-based operation system where it's effectively issuing mapping commands over files located in a file store, Spark's approach is to load once into memory from source system, which is disk, and then do all of the operations that it needs to do in memory. And that includes calculations on the data, joining of data is all done in memory. And you don't have interim stages, or at least you don't need to have interim stages that are materialized and checkpointed to disk. There are times when you can do that, but that's not something that's required. And because everything is in memory, this opened up this amazing possibility that the people at my company at Databricks early on, when they were working through that very early version that Matei came up with, and the other founders of Databricks were working on at the AMP lab in Berkeley. This in-memory processing allowed for an incredible amount of optimizations to happen, in which that eventually moved into systems that exist within Spark, like Catalyst and Tungsten, that allow you to issue basically DML instruction code from a number of different languages and optimize those instructions in such a way that it can become incredibly efficient. Now, if you were going to do something in, let's say we're doing something in base Python and we're operating on CSV files that are sitting on our laptop in some folder. When you want to do an operation on that, and all of your data is in a single file, there's no real difference between that and any other system like how Spark would do it. You load the file into memory, and Python's going to do operations, whatever you're telling it to do, And when you're done, you're going to write data out somewhere, or you're going to display an image, or whatever it is that your code is doing, it's going to do that. The optimization comes in when you're actually having to do things that are not a demonstration or going through a tutorial. Real world problems where it's like, all right, what do I do when I have to join 37 data sets together in order to create a feature set? Or what happens when I have to issue operations where the interim state of that operation wouldn't fit into memory on my computer, where I would just completely fill up my RAM, the program crashes because there's no more usable operating memory. So systems like Spark can look at the stages of operations and break and chunk those up into tasks. And this allows incredible scalability of use cases on the platform. So you can do things like, train a model on terabytes of data, even though you don't have the ability to spin up a single machine that can hold that much data in memory, or doing ETL processing of petabytes of data. You're not going to be able to spin up a VM anywhere in the cloud that has 50 petabytes of RAM and the number of CPUs required to handle that processing in relatively short amount of time. So that whole distributed nature of that architecture lends itself to large scale computing tasks. But there are other things that Spark can do for ML that are not relegated to big data. And that aspect is something that whenever I've had conversations with people about using Spark for something that it doesn't seem like it's designed for, they're like, well, I only have, 50,000 rows of data and 20 columns. It's not that big of big data. I'm like, yeah, but you got to tune that thing, right? They're like, well, yeah, I have to tune it. I'm like, well, let me show you something. Instead of you doing a for loop on your machine on a single VM, let's distribute that. Let's copy that data, that small data, to 20 machines. And let's have each of those do an optimization iteration of, an optimization algorithm. Let's see which one wins out. But let's look at the wall clock time when we have 20 machines doing 20 experiments in parallel.
Yeah, so that transitions nicely into one of my questions. Often you have scenario. So take an example of writing a bootstrap algorithm. You have one base piece of data, and you need to create small variations and small versions of that data, ideally in a parallel setting. So an example, in a non-parallel setting, write a for loop, do your operation, take the mean, output it to an array. Very straightforward, but you could theoretically increase it by nx speed, where n is the number of clusters that you have. How would you go about doing that then?
I wouldn't do it by number of clusters per se. It would just be the number of workers.
Yeah, excuse me, I meant cores.
Yeah. So we would take whatever that base data is that we need to do a generative operation on, and we would write a function that contains the logic of whatever we're trying to do. So our seed state is our data itself. And then you could also introduce ranges of operations of things you wanted to do. You want to do a pathing algorithm. Well, you can set a first stage of operation that seeds out to different executors and saying, if we're doing traveling salesman problem and we're going from, Chicago to Dallas, what's the most efficient way to get to London? Well, we could say, okay, from Chicago to Dallas, do we want to go Atlanta? Do we want to go Albuquerque? Do we want to go Denver, San Diego, Los Angeles? Each of those first stage steps that we would take, we can push those out to different executors. And then they can handle it from there and say, all right, now do your iterations independently on each executor in parallel. So it gives you the ability to minimize that, like a first round of iteration, which can dramatically increase performance and scales to however many machines. Exactly as you said, the n number of workers that you put on a cluster is going to make that just go that much faster. That's an interesting scenario that you brought up, because that's one of the hardest problems to optimize when computationally. The space complexity and the computational complexity of those sorts of Markov chain problems they're expensive no matter where you do them. The goal is, where do you set your boundaries when you're doing simulations? If you're doing stuff like, all right, I got to do causality analysis, I want to run a bunch of simulations and see which one actually points to a likelihood of being the root cause here of this behavior that I'm witnessing. the only way to solve it is brute force. And the only way to make brute force go faster is in a distributed environment.
Got it. And you also mentioned another thing that made Spark effective in that a lot of the Hadoop and MapReduce operations worked on disk. And Spark completely transformed all of its operations to memory. And I was curious, when I was learning about Spark, I was curious what the difference is. And reading 1 megabyte sequentially from memory is 100 times faster than reading 1 megabyte sequentially from disk.
Mm-hmm.
So by keeping everything in memory, those operations become a lot faster. And obviously Spark has a lot of back-end optimizations as well, but fundamentally keeping everything in memory, I would argue, is one of its main claim to fame because it allows for a lot faster processing than most other paradigms.
Oh yeah, big time. In modern day cloud-based implementations like on Databricks Spark is not going to have that same relationship. It's going to be much faster than the Hadoop comparison or the disk versus memory comparison. There are optimizations that have been put in place that make every stage of the journey, not just accessing data being faster, but optimizing kind of, as you said, like the optimizations that's in there on top of the in-memory processing, the stuff like figuring out how to minimize unnecessary shuffles, figuring out how to optimally manage the garbage collect processes on objects that are no longer required to be held in the heap on the JVM, and that rewriting of your code part of it. It's not actually rewriting. It's not like code generation, unless you're using AutoML on Databricks, then it is. But if you're talking about the execution, because it's a lazily evaluated language, that's another reason why this is so important for its performance. You can send it. I think it would be easier if I explained like how it would work in say a Jupyter notebook. You go in through, you're writing a bunch of operations in a Jupyter notebook, and you're executing cell after cell after cell. First cell is read data file from CSV, and then second cell is, instantiate a model and do some feature engineering work, and then we're going to train the model. Each of these operations, they're actually getting executed. It's a greedily evaluated language. It needs to execute line by line in order to maintain state in Python. Now, when you're talking about Spark, it's only going to evaluate everything that you've told it to do, even if you're in an interactive REPL, like in a notebook on Spark. It's only going to evaluate and execute anything once it has to. Once you tell it to do an operation like write data out or display something on screen or calculate the training error loss. Those are actual execution barriers. But everything that went up to that point, it's all code that Spark is able to do whatever it wants to do in order to optimize what you told it to do. So in the case of, hey, I have 15 tables that I'm joining. I wrote a whole bunch of SQL to do these joins. Well, the chances that you're going to write that SQL in a perfect way that's going to be performant for the execution that needs to happen, pretty much slim to none. Even if you're an expert at SQL, what Spark's going to do is going to look at all of those operations that you've told it to do, and it's going to say, well, it's going to be more efficient if I take data source number 1, join it to data source number 17 first on this inner join. And then the result of that, I'm going to do a left outer join with these other 8 data sets. And then I'm going to do a skew join or a broadcast join or something. It's going to look at what the most effective way is to materialize that data set, and we'll use that instruction set accordingly. So it's sort of a smart engine for that.
Yeah, lazy evaluation is really effective. And I have found that it actually does not impact my workflow at all. Theoretically, you would want intermediary steps along the way, but if you're just thinking critically about what the end result needs to be, and you have something that will optimize how to get there, that's, really, really powerful. You don't really need to think about the intermediary steps as much. So I've really enjoyed that aspect of Spark. So I also thought it would be useful to, before we get more into the ML side, to talk about how exactly Spark works in terms of distributing work across different cores. So there's often a breakdown where we have a single master node, and then we have a bunch of worker nodes. And how is data and work transferred between the master and the worker?
Ooh, excellent question. So data isn't. It shouldn't be. There are cases where you would say, I have data on my worker nodes, which is where it should live, but you need to do some operation on a subset of that. So you do a collect. Collect is telling the executors, the workers, saying, hey, I need your data. I need a copy of it, at least. So please send it over to me, and I'm going to do some operation, and I'm going to tell you what to do later on. It's very dangerous to do that if you don't really know what you're doing, simply because you can very easily overwhelm the driver. If you collect too much data to it, you can fill up the heap and it can crash. But there are plenty of times, I've done it thousands of times, where I actually need to collect information. I do a group by and aggregation. I want to get, some sort of dictionary that I can then operate on in the next stage of the code. Well, the driver actually needs to know that. And what I mean by the driver needs to know that is that the driver is the only one that actually knows what's going on. So the driver is where your code executes. The workers, they're clueless. They have no idea what is going on. They don't have access to the instruction code that the user is submitting. They're just processing RDD tasks that the driver tells it to do. And what I mean by an RDD task is that's what the workers are actually doing. So we have this notion of a resiliently distributed data set in Spark. And under the covers, it's basically just a sequence of collection files. So when we're looking at data as read on a machine in a particular language, so we're in the JVM on Spark, and when we're looking at a row of data, that is a strongly typed association of sequences. And those sequences are what we call rows, but that row is just a collection of types. So if we have user ID, day of year, and year as 3 columns of data in a table, under the covers to Scala and Java, that's just an array of arrays of long integer. And when the RDD aspect of that is we have a concept of provenance of where each row comes from. So we have a linkage to the source system saying, hey, I know where this row came from. It came from a partition that was located on disk at this location. And then usually we're talking about object store. Like it came from this part file on S3 or ADLS Gen 2. And we can do operations on that part file on any of those executors. It's basically whoever picks it up, whoever's the one that actually ends up reading that partition, we're going to execute arbitrary code from Catalyst, if we're using the data frame API, and do some operation. Maybe we're mapping over that, or maybe we're doing a fold over that, where we're calculating some sort of interim state of aggregation as we're going over some primary key that we've submitted. Whatever the operation may be, at the end of the day, we're just talking about manipulating arrays of arrays. And that's really all it is. But the RDD aspect is that each part of that meta array that wraps up that entire data set, collections of rows are distributed to different machines. And that's what the RDD aspect is. So we can have a command and control machine, the driver, that can talk to n number of workers and tell them, hey, you need to take these parts of this larger data set and do this operation on them, and then tell me when you're done. And then the driver waits for the return from each of the workers saying, yep, I'm done. I completed all my tasks. And the driver says, okay, now I need you to do this operation on this data. Or, hey, you have some data that you need to send to this other machine. So go and do that and tell me when you're done.
Got it. So you mentioned that data are distributed onto worker nodes. Mm-hmm. 2 questions. The first, so these are called partitions. They're partitions of the data, and they're often partitioned by rows. So you take a column, and let's say if it has 3 unique values, it might partition that data set using each value. So value number 1 goes to this partition, value number 2 goes to that partition, value number 3 goes to this partition. 2 questions related to that. First one is, let's say you take a data set and you don't specify any partition key. How are data partitioned by default?
The internal method of a repartition is it's just done by a hash key, and it'll figure out what the most efficient way of doing that is. But it's kind of expensive to do that. And I've seen that in people using Spark before. They're like, oh, I'm just going to do a dot repartition, and that's going to shuffle all my data around and try to balance things out. And a lot of people don't look at what the signature is of that function or that method, where you can do a bunch of different things with that. You can try to enforce that key location or co-locality of a particular grouping key. You'd say, hey, repartition by this column and attempt to co-locate all of that data. By the way, that is a shuffle, and that is exactly what a group by key is actually doing under the covers. Just saying, hey, put all the data for this key on this worker and then put all of it on another one. But if you don't specify anything other than utilizing the default of partition count, which is set at the Spark session level, which is defaulted as 200, you're just going to get 200 partitions across your cluster that are going to contain data, and it's going to attempt to balance it out by estimated size.
Why do you partition by row and not by column? So why are rows split up instead of columns split up?
Man, that's a good question.
Hi, this is Charles Max Wood from Top End Devs, and lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. You know, whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
That's an architecture question for why Spark was designed in the way that it was, which is in order to get the maximum amount of parallel computation that you can while maintaining the ability to reference other elements of a contained data vector. You want to make sure that all of the column data for a row is referenceable by that column. So if you have a row of data that is user, date, some other IDs that are in there and some double value, if there's some conditional logic that you need to apply to add a column to that, that's going to allow you to calculate something new. Most of the conditional logic you're going to have is going to be referenced by that particular row of data. So you would be referencing those other column positions. So it's really critical to keep that as its own thing. All of it is married together forever unless you explicitly say, hey, drop this particular column across the entire data set, or you add new things to it. But the only way to really separate that concept of column-wise operations is to transpose a table. And there are ML algorithms that do that on Spark, that do matrix transpositions. They're really expensive, just be warned. But they're in the MLlib API, the RDD API. You can do all that stuff in Java and Scala.
Got it. Okay, cool. Because it makes perfect sense that you would want for SQL-like operations to have sort of a mini copy of the data set where different columns can interact with each other, because that's what most of the transformations would look like. But I could see scenarios where you would want a single column onto a single worker. So good to know that is theoretically possible.
I would call that really advanced Spark programming to do stuff like that. I wouldn't even attempt to do something like that with the data frame API, just because it's really not designed for that. But in the RDD API, you're exposed to extreme low-level APIs with Spark. And provided that you're comfortable with digging into source code and really understanding how a lot of that stuff works, you can do some pretty extremely low-level things. Like you can directly access BLAS operators if you want to through Apache Breeze. And you can implement your own version of a matrix transformation if you so choose. It's all open source. It's very hard to do that and to get it to be performant, but it's possible.
Cool. So I was thinking that we could potentially go through some of the key topics, and then as this is a machine learning podcast, start getting to more of the ML components. Question number 1 relates to Spark SQL and some of those transformations that are fundamental to what Spark does really well. So I was wondering if you could walk us through what is an aggregation and how they work under the hood.
An aggregation in Spark SQL. So we talked through what a group by basically is. It's that repartitioning of, if I want to know how many people are alive in America right now by state, I say group by state, and I want a count of humans in each state. What Spark is going to do is it's going to instruct the executors to figure out basically how many entries of that key state exist on each executor. And it's going to tell each one count's not going to require a shuffle, but a count would just require
average.
Yeah, it would just iterate through each of the collections that it has, and then at the end report back. But
so let's take average.
Yeah, average would be
number of humans.
An average, or the most expensive one would be a median calculation.
Sure.
You would have to co-locate the data first. So however many workers that you have, they're going to try to balance out one another to get the data that it needs to answer that question. And then on the executor itself in the RDD operation, for an average, that's relatively simple. It's just going to do a sum in Scala over that particular value and then divide by the count. Median's a little bit trickier. So that's going to have to basically copy that collection and sort it. And that sort order that it returns, it's going to have to get the midpoint of it. So that's why that takes a little bit longer to run.
Let's say we're taking a median and we have an extremely large data set. So let's say we're grouping, we have 100 million rows. The key that we're grouping by has two distinct values, so it's called 0 or 1. Let's assume that all of the zeros and all of the ones cannot fit onto a single execute. What happens then?
For a median value or for what?
Sure.
You're going to get into a condition where everything's going to slow down like crazy, because Spark has a mode where if you don't have enough memory available to perform an RDD operation, it's going to do interim spill. And that means that it'll start chunking up the processing step that it needs to do while using an accumulator locally. So it's basically doing a fold left or a fold right on the operation. And in order for it to process data that it can't fit into memory, it has to write it to local disk on that particular executor. And as you said before, that 100 times slower, it really is. It's very, very slow. And what you usually see this happen on is somebody doing a sample on, like, for an ML task. And they're like, well, I trained my algorithm, or I did my feature engineering on a sample of the data to make sure that everything worked. And it was like 2% of the full production data set. And then it was so fast, it ran in like 5 minutes. And then they try a training run in staging environment against production size data. And they see that it's taking days to run. And they ask an expert, they come in and they say, well, open up the Spark UI. Let's look at what's actually happening. And you look at, the executors, and you see that terabytes of data are being spilled to disk. And the solution around that is to don't spill to disk. Any operation that you do, you should be sizing the cluster appropriately large enough to accommodate that. And there's ways that you could solve this particular problem that we were just talking about, where you have a skew problem where to answer that problem where you have too much data that will not be able to fit on a single executor. Well, is there a way that you can chunk that data up? Like, do you need to have that average of that value or that median of this particular key that has 10 terabytes of data in order to satisfy that? Do you really need that? Or can you chunk that operation up so that you can split it out across a bunch of distributed machines? And there's clever ways of doing that, like salting the key and doing that interim calculation, and then at the end you're doing a final much smaller operation on like a summary of the summary data.
Got it. So theoretically, if we were calculating median and it did not fit, all the data did not fit onto a single cluster, but it fit onto four. Second time that's happened. So it did not fit onto a single core, but it could fit onto 3 distinct cores. Does Spark have a way to distribute the top third in terms of rank to one cluster, the middle third to another cluster, and the bottom third to another cluster? Or does it have to do all of that on one core, and then if there's not enough space, spill that to disk?
It depends on the instruction set. So certain operations, you have to co-locate the data, and the only way to answer that particular question is to have all of the data in memory that a single core can access. But there's a lot of operations that can be distributed. And Spark's default operation mode is if it can be distributed, distribute it. If it can't, and it's an expensive operation, sometimes you'll actually get a warning in the Spark UI. Like when you execute something, it's like, warning, you might not want to do this. And in the documentation, things like that are usually called out pretty explicitly about like, hey, this is a really expensive operation. You might not want to do this. And you'll see implementations that like in Spark MLlib versus Spark ML. One's the data frame API for Spark ML, like distributed machine learning. The other one is the RDD-based API. There's not parity between those two. The reason being is it's incredibly challenging and complex to get some of the RDD APIs to work with the data frame API because of how decisions are made about how to shuffle data around and how to optimize operations. And thinking through that, take of that what you will, about how certain ML tasks, it's not that it's impossible to do in an optimized way through a high-level API. It's just there's not enough justification for the effort required to implement that.
Got it. That makes a lot of sense. How do joins work?
Magically. It's all about it. It's not that different from how it works on an OLAP database, where you have some semblance in Spark of a schema associated with any data set. That's why a lot of the first things that you do when you read in a data set is tell it which columns are which and what types they are. You can have it infer it, and that's what it'll do if you don't specify it. But it has a general metadata understanding of that data. It knows, where each part of the data exists on each executor. It knows which rows are where. But the key aspect of it, of knowing what that type is, allows it to understand what it can and can't do with that sort of join operation. But if we have two data sets that are of equal size, that are distributed out across a bunch of workers, we're going to look at the values that exist within those keys on each executor, and there will be an optimization stage where it will determine there's a way that open source works and there's the way Databricks works. I have to be careful about what I explain here, about which one works in what way.
It's fine if you make a mistake. We're not worried.
But there's some very clever software that has been written that allows for like a phased approach for this, where it'll do computations and evaluate what the expectation will be and adjust dynamically as stages are executed. And we'll say, well, I have all the keys that satisfy this join on executor 1. I have 80% of the keys for the second key on executor 2, and then those other 20% are on executor 3. It'll prefetch from executor 3 and say, hey, put the data over here on executor 2, so that when we do this join, we don't have to, do any additional shuffling. So the system tries to minimize the amount of shuffles that need to happen. And once that is sort of satisfied, it'll start doing that join. And that join is exactly what you might think it would be. So how would you concatenate or, intersect lists in Python? You have a list with common keys, or you can think of it as a dictionary in Python. If you're going to say, hey, I want to take dictionary A and I want to combine it with dictionary B, any keys that exist are going to be persisted between them.
It's almost like creating a set.
Yeah, it's actually exactly what it is. So in Scala, that collection they're all immutable under the covers. So it's not like you're actually mutating and modifying that RDD. You're making a copy of the intersection of those two sets, and then there's some filtering conditions that say, hey, if I say I only want these 4 columns out of the 200 that were part of this pre-join of these two tables, it's going to pre-filter on those things. It's going to say, hey, drop the other 196 columns. I don't need those. And now intersect these two and give the result.
Got it.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
Cool. So we're already at 40 minutes, so I think we're going to be skipping the ML portion, saving that for next round. But
Sure.
there's still a couple more things on architecture and sort of data transformations. Another question that I have is, what is MPP architecture?
I mean, MPP is massively parallel processing, and that's effectively what, Hadoop or Spark is. It's the concept of you can almost infinitely scale the problem to a certain degree just by adding additional execution machines for the data processing. You have a single command and control or a group of command and control machines that are determining what those subordinate machines are doing. So you can just distribute out the work and operations. It's still limited by Newtonian physics, though. I've heard people tout like, oh, there's no limit to how big you can create a Spark cluster. Like, yeah, there's always a limit. That being said, I have seen some truly astronomically large clusters started during my time working at Databricks that contain more worker nodes than I thought were possible. And you typically need
What's the most you've seen?
The largest cluster I've ever